Okay. Hello, everyone. Thanks a lot for joining today for the CMU Bharat seminar series. And we are very fortunate to have Professor Olivier Doré as our speaker today. And Professor Olivier Doré is a principal scientist, group supervisor in JPL Caltech, also a senior faculty associate in theoretical astrophysics at Division of Physics, Mathematics, and Astronomy in Caltech. He did his PhD from Institute for Astrophysics in Paris in 2001. After that, he was postdoctoral fellow in Princeton, CETA, and so on. Professor Doré has been awarded several prestigious awards such as JPL Mariner Award, Gruber Cosmology Prize in 2012, 2018. Also, the Breakthrough Prize in Fundamental Physics in 2018, and JPL Explorer Award, and many more. He's the project scientist for SPHEREx mission and Nancy Grace Roman Space Telescope, for which he's leading the team focused on cosmology with large-scale structures. Other than these two experiments, he has been involved in several other experiments such as SPIDER, Planck, HFI, WMAP, Euclid, and LSST, Dark Energy Science Consortium. And today, Professor Doré is going to talk to us about the SPHEREx mission. Over to you, Olivier.
Okay, thank you so much. And first of all, I want to apologize to all of you for wasting a bit of your precious time last week by making a really embarrassing mistake about dates. So I hope I wasted a little bit of your time, but hopefully it was worth the wait. So, and I hope this talk will interest you. So it's a virtual talk, so it's not the same, but I really want to encourage you to interrupt me and to ask questions. And feel free to, it's not, the more interactivity, the better. So feel free to stop me anytime. If I miss any raise hand or any question in the chat, please feel free to report. Okay. So today I'm very happy to present to you on behalf of the SPHEREx team, the SPHEREx mission, and I will give you a quick science overview, and I'll also give you a quick status. And so what is SPHEREx? So SPHEREx is what we call a medium-sized explorer mission, which is a class, so it's a NASA astrophysics mission. It's actually the next NASA astrophysics mission to launch. It's scheduled to launch in early 2025, actually, February 27th to be exact. And so it's a class of mission which is among the smallest NASA mission in astrophysics that exists, but it's also it's a very more frequent mission class. So it's a class that enabled very successful mission in the past. For example, you're all familiar with WMAP or WISE or NORTES, who's still operating. And so the next of this mission will be SPHEREx. So it's the same class, same principle. And the principle which is made it so successful is that it's competed. It means it's an open competition. Any university, any group of people can apply in the US. And it's led by a PI. There is a cost cap, so it means there is a budget which is allocated, defined in the call. And if you go over this budget by $10, you will be canceled. So it's a very strict cap. Well, it's not as simple as that, but that's really the spirit. There's a strict cap, which does not include the launch. And on this, and it's on a very fast schedule. So it's like we were selected, for example, this mission was selected in 2019 and we launched in 2025. And this is despite COVID. So in principle, it would have been a little faster if it was not for COVID. And so it's a very interesting class. And I think the fact that it's competed and the fact that everybody can apply means that it's very diverse and very, very dynamical. And a lot of news, every time there's kind of a new idea that is proposed, so which makes it so this program so successful. I want to say also to just quickly that the latest UVEX has been selected like a couple of months ago, and I would started implementation a couple of months ago, which is a UVEX mission, which will be a UV all sky survey, which is also very interesting. And yeah, and I think that's it. And if you want to know more about this program, please have a look at this Explorer website. So, okay, so that's what enables SPHEREx, but so what is really SPHEREx about? SPHEREx is really designed to address the most important questions in astrophysics, at least as defined by NASA. And so the first one we'll address directly is really, how did the universe begin? And we will address this question by probing the physics of the young inflationary universe. So it means probing inflation physics through the 3D clustering of galaxies on the larger scales. The second question we will probe is how did the galaxies begin? And we'll do that in particular. We will probe the epoch of ionization. We will study the cosmic history of light production through near-infrared background fluctuations. So we'll do very in the regions we observe very frequently. We will be able to do very reliable, deep, diffuse light mapping, and we will interpret this map and look for signal of ionizations, of the ionization. And finally, the next question that really defines SPHEREx is what are the conditions for life outside the solar system? And we address this question by studying the Milky Way for water ices and other molecules which are essential for life as we know it on Earth, so other biogenic molecules. And to summarize, SPHEREx will probe in novel ways the origin of the universe, the origin of galaxies, and the origin of life. And in the process, we will actually construct the first all-sky near-infrared spectral survey. So SPHEREx will be really first all-sky spectroscopic survey. I think maybe the second after IRAS, but it's obviously very different. And if there's one thing that is you should remember, I think that we should remember from this talk, is the fact that it's kind of data set that we will deliver to the community very, very quickly after launch. And so what does it mean to be a really all-sky spectral survey? It simply means that for every pixel of the sky, 6.2 arcsecond, we will measure a spectra. So we'll have a spectra, low resolution, near-infrared spectra, so R about 40, R being the spectral resolution, so lambda over delta lambda. So we'll have an R about 40, between 0.75 micron and 3.8 micron, and then we'll have a higher frequency wavelength resolution at higher wavelengths between 3.8 and 5 micron. And so it's really for every pixel, you will measure a spectra. Whatever is in this pixel will have a spectra. And so you can think of it, so it's low resolution spectroscopy. So you could also think of it as somewhat as fine photometry, like small narrowband photometry. And so another way to think about our data set would be to think of 102 all sky fine band photometric map at 6.2 arcsecond resolution. So it's very clear already by thinking of this data set that it will be a very large impact, and it's an unprecedented data set, and it will cover a lot of astrophysics. And that's really what makes this mission unique and I think very exciting. So it's not enough to specify. Yes.
Can I interrupt just one sec?
So, of course.
First of all, what is the R that you are mentioning in this? What is the quantity R?
Yeah, R is a quantity that specifies the spectral resolution. So it's for a spectrometer or an instrument. So it's really lambda over lambda over delta lambda. So it's a width, if you want, it's a width of your, bandpass, if you want.
I see. And what are the two R's that you are mentioning here? The two sets of R's.
Right. So the two R's correspond to two different. We have a varying resolution according to the wavelengths, and so between 0.75 and 3.8 micron, we have R of about 40, and at higher wavelengths up to 5 micron, we have an R of about 130. So it's just by design we need, and I'll explain that later. It's like we need to have a higher resolution at high wavelengths for reasons related to the IC's investigation that I will detail later. Does it make sense?
Yeah, thanks.
Okay. All right, so now we specify the magnitude. We have this all sky survey. For every pixel, we'll have a spectra. So how deep will the spectra be? So what you see here is a plot which are coming from our proposal. So you see the 5 sigma magnitude AB, which is the sensitivity, the point source sensitivity as a function of wavelengths. And you see SPHEREx here, so we have naturally the way the survey operates, we'll construct the all sky survey. And since we will be in low Earth orbit, we will be looking at the north and south ecliptic poles very regularly. So we'll go deeper in this pole, and we call that the deep survey. And sorry, so there's a question in the chat, but if I should answer, let me know. And So in the all sky survey, so you see the depth as a function of wavelengths for the all sky survey, which correspond to this point here, this black point here, and this for the all sky survey. The deep field here, you see this little, this orange envelope here, and the width of this envelope really corresponds to different assumptions about our performances. You have the higher the sensitivity, and the lower is slightly less optimistic assumptions, and we will be a little shallower. But typically you see that we are about magnitude 20 for the all sky survey and magnitude about 22 for the deep survey. And this is for every single frequency element or wavelength element. So that's what each black dot here, or here correspond to a different frequency element. So it means that you have a really very uniform depth, and you have this spectral resolution. So to give you an idea, this band as a reference point, we have here the all WISE depth, which all WISE is an extended version of the WISE dataset currently available. And you see what typically we are about as deep per single frequency element. We are as deep as all WISE, meaning that another way to think about that, it means that we will have a spectra for every WISE sources. So we will get spectroscopy of all the WISE sources pretty much. And then in the deep field, we'll go even deeper. And for reference here, you see also the pan-stars points, which are deeper, but in optical. And then you see here the depth, for example, of the Euclid spectroscopic survey, which is in a corresponds to I-band. So anyway, so that's interesting about this plot. That's forecasted. That's what we forecasted when we wrote a proposal. So this plot was generated actually in 2018, but we now have built instrument, we have tested instrument, and the expected performance really matches this curve and actually are right above the top of this curve here. So currently the instrument performances as we measure them in the lab match our optimistic expectation, which is obviously a good place to be. Okay, so it's not obviously not enough to have a great instrument. We also have a great team, and this survey is really enabled by this team. So you see the team is led by Jamie Buck at Caltech, who is a PI. I'm the project scientist of the mission, and you see that there's a very big. So you see it's a pretty small team for such a mission, so which is by design. So we constructed a small and focused team, and there is people are located, a lot of it in Caltech and JPL. There's a group also in Irvine. There's a group in Arizona. There's a group at CFA, and then an important group in South Korea in CASI. So through the South Korean Space Agency, CASI, and the project management engineering team is centered at JPL, and the spacecraft was built and assembled at Ball Aerospace, no BAE Aerospace. And you can see pictures of the team here. You see that it's overall a pretty small team again. And so, okay, so now the question is, what will we do with such a data set? What can we do? So it's because it's an all-sky survey, the science we will enable is very diverse. And so if you think of it as all-sky survey, so we expect, I guess, whatever, we'll have a spectra of all the astronomical objects we are sensitive enough to see. And so for this reason, we'll have all kind of wonderful and diverse objects. We expect spectra for more than 1 billion galaxies. Among these 1 billion galaxies, we'll have medium accuracy redshift, which is redshift better than 10% in sigma z over 1 plus z for more than 100 million galaxies. We have high accuracy redshift measurement for more than 10 million galaxies, which is accuracy unit. So this high accuracy typically is accuracy you need to measure. DAO will see more than 25,000 clusters, and we'll be able to have a redshift for some of these clusters. And of course, we'll see many, many stars. We expect more than 100 million stars. We expect, since we are very all-sky survey, of course, we are very good at finding rare objects. That will be very small. That will be harder to find with a smaller field of view. And so we have, with a smaller survey, I should say. And so, for example, we have a lot of dust-forming stars, a lot of brown dwarfs, a lot of cataclysmic stars, a lot of also high redshift quasars, even though our sensitivity is not very, very deep. Actually, high redshift quasars are very bright in the infrared. So if they are, we would see all the known quasars at redshift greater than 7, and there are more of them. Hopefully, most likely they are. We'll see them. We also expect to have spectra for all the known asteroids of comet, which actually more like 100,000. And we also do interesting survey, interesting lag regarding, for example, H1 mapping in the galaxy, or H2 mapping, or pH mapping, etc. So it's going to be a very rich data set. We expect this kind of historically, this kind of all sky survey really led to very high scientific returns. And that's, you can see of the impact of COBE or IRAS, of GALAX, WMAP, Planck, or WISE, and hopefully SPHEREx will be in this tradition, will continue this legacy. And so something we really embrace is the fact that I mentioned we are very specific investigation. We want to address very, very specific questions. So it means that all of our data, a lot of these discoveries, a lot of these interesting objects will be discovered by the community. And so we fully embrace this. And so we develop what we call the conveyor belt model, where we actually, and this video shows you that it's not actually, doesn't mean a simple model, but it's really a model to deliver all data to the community very quickly. So I guess, again, we launch in early 2025, so in a couple of months, really. And we have 1 month of commissioning. And after that, we are committed to release our calibrated image every 2 months, within 2 months of collection. And we'll do that throughout the mission. So in practice, we expect that every week, we will release the observation from the previous week, calibrated and register, so you know where you're looking at. So you can download this data, you'll be able to do science already. Every 6 months, we have complete full sky survey, and so we release full sky products like lower either data cube or low level or first the catalog, sorry. So low level, we will really release all the exposures, processed uniformly, and then also data cubes. Every 12 months, after 12 months, every 12 months we complete 2 sky survey, which enable a lot of consistency tests, and so which enable the validation of source catalogs. And so we will release our first source catalog within 2 months of the 3rd survey. That will be a first major release. And at the end of nominal mission, after 2 years of observations, we are supported for 1 more year of analysis. And at the end of this period, we will release all our science, so science paper on all the catalogs with redshift, all the maps of diffuse light, and all the scientific papers. All this will be done within 3 years. So it's a pretty fast pace. It's going to be intense years for sure. And all this will, all the data products will be hosted at IPAC, which is an archive center on the Caltech campus, which is the same center that hosts and deliver, for example, the Spectra data set or the WISE data set. Okay, so the current status, as I said before, we were selected in February 2019. After that, we went through multiple phases of design, and then phases of fabrication. And now we are what is called in NASA lingo, it's called phase D, where we do the final assembly, final integration, and we are in the middle of a very thorough testing program. And we are getting ready to launch again from SpaceX Falcon 9 in late February. That's the current schedule. And after that, 2 years of operation for 2 years of operation, and then 1 year of analysis. Okay. Okay, so let me now give you an overview of the science goal and the science. Yeah.
Olivier, can I just ask a curiosity question? How many proposals were vying for the same slot when SPHEREx was selected?
Yeah, I don't really know, because actually that's not something which is being shared. But I think it's typically between a little more than 10, between 10 and 15, I expect. And so it's a 2-step process. So there's a phase A and then a phase B. So the first phase B, I think I expect between 10 and 15. And then two are selected for phase B, which is a 1-year study where you receive a little bit of, some funding from NASA to do to refine your study, your proposal, your concept, 1 more year. And 2 missions were selected, and then only 1.
Thanks.
Yeah. No, it's an interesting process. Yeah.
Mhm. I was asking because ISRO is also getting more interesting science missions, and I wanted to see how your processes work versus how things can work.
Yeah. So that So did I answer your? Sorry, did I answer
Yeah,
your?
No, perfect. Yeah.
Yeah.
No, so, yeah.
And so I guess yeah. So I don't know. All this is very very regulated. So information is very shared information is very controlled. I know the second mission that was selected for phase B was a X-ray mission. So totally different science, totally different design. So it's really it's a difficult choice for sure.
Thanks.
Okay, so how this is SPHEREx as it was designed, and that's really I'll give you an overview of the instrument. So it's overall it's a fairly small spacecraft, I should say. Like the overall height of the spacecraft about 2 meters, which is more or less it's a virtual talk, but that's it's actually more or less my height. But the key there are three, let's say, three characteristics. The first one is a very small so okay, what you see here, you see the telescope here, which is a 3-mirror astigmat design. So the lights come here, goes here, here, and then bounce to the detectors. And the detectors are here, and there's a beam splitter here. And so, but it's what's remarkable is, what's unique, that's remarkable, but what's unique is the fact that it's a very small mirror. It's only 20 centimeter of effective aperture, but it's a very wide field of view. So it's really a very fast optic. So it's really a survey machine. So it's really, again, 20 centimeter, but in space, cool, but with a very wide field of view. So about 40 square degree. And so it's really a very fast survey machine. The second key feature is the fact that it's a passively cooled, so it means it can operate a long time. There is no cryogeny. It's just a collection of radiator. On the telescope, is expected to be at about 80 Kelvin. On the focal plane array, so the detectors will be about at 55 Kelvin. And this is really feasible through this. It's a carefully, of course, designed thermal system. And you can, Tarun will recognize here this kind of structure here, which are called V-groove, which are really directly inspired by the Planck design, so a structure that will absorb the heat, and the radiation will be radiated away in this successive what we call photon shield. So like the heat will be dissipated here and then scattered and radiate this way. So that's really and that's really happening through this V-groove, what we call V-groove radiator, if you want. So that's the second feature. And the third feature is the fact that we will do spectroscopy without a spectrograph. We'll do spectroscopy through very specific filters, which are called LVF filter, linearly varying filters, and I will detail what they are. But so that's really what makes this mission possible, what makes the survey very efficient, and that's really what unique design feature of SPHEREx. And finally, the spacecraft will be in low Earth orbit, and the spacecraft is provided by BAE system, formerly known as Doré. Okay, so that was the design. That's how it looked. It looked beautiful, and that's how it looked in Caltech in the basement in September 2023. So you see here again the telescope. You see the V-grooves I've just mentioned here on the bipods, supporting structures. Really, it's like they are green here, but they are not green in reality. And you see the V-groove on the telescope. So that's really how it built, and that's remarkable. And the instrument is that it's small enough. And because it's a small-scale project, it actually was assembled and tested in a vacuum chamber in the basement of the Caltech Cahill building at Caltech. So which is pretty remarkable and really, really handy. So you can really have the instrument here. So it was tested there, and now that's how the mission looks like as of a couple of months ago, April 2024. That's really fully assembled at BAE. You see the conic shield, the telescope here with a cover, the spacecraft here. So, and then this was being expected, it was being looked at, and this is before it underwent intense testing phase, and it's actually finishing right now as we speak what we call the thermal vacuum test, where it goes into a huge chamber which goes simulate vacuum and the coldness of space. So that's happening now, and it also underwent overall a pretty intense testing campaign. One of the very intense and spectacular tests is really what is called a vibration test. So you see here the shield structure being shaken to stimulate the launch and make sure that everything works well. And you see that it's a pretty violent process, very stressful to watch. It really moves a lot, and that's really, again, it's just to simulate the launch. And so the instrument, like the payload, is being characterized in some way before, and then it's being characterized, then it's being shaken, and then it's characterized after, and everything went well. So it's a very strong, it's small, but it's a very strong structure that can really withstand this kind of vibrations. So it's a pretty impressive setup. Okay, so let me talk now about the spectroscopy, the way we do spectroscopy. So it's really, again, as I said before, it's really, we do spectroscopy with linearly variable filter, which is really spectroscopy without a spectrograph. So we have 6 detectors, so 3 detectors separated by 3 detectors with so we have a beam splitter and 3 detectors on each side, which are mirrors of one another. And in front of each detectors, we have what you call LVF, linear varying filter, which is a filter, and the transmission of this filter vary as a function of position. And you see here in this picture, which is doesn't come very well, but again, you have this filter which is fixed in a focal plane, and because of the property of this filter, each row of your detector will see a slightly different color, right? So you will measure in each row of your detector slightly different colors. And so the way you will construct a spectra for every single pixel is by simply moving the focal plane, so moving the spacecraft around. And so you don't construct a spectra instantaneously, you will construct a spectra in post-processing by combining your images. And that's what you see here. For example, if you wanted to take a spectra of this object, you will have to make sure that this object is observed at all this location in the focal plane array. And then you build a spectra with time this way. And so really the spectra are obtained by stepping sources over the field of view in multiple images, which is what this animation shows. So the advantages of this design, the fact that there is no moving part, you just move the spacecraft, so which is a very good thing for a space mission. So it's a very simple design. Then it's because it's a filter just in front of your detectors. It's a very high throughput, so it's not a spectroscopy. It's a very high throughput design, and then it means that the survey is designed just to repeat, to scan, the survey is designed so that every pixel of the scan will end up scanning the field of view this way. So that's a very interesting and powerful design for a space mission. And that's something which is actually new or uncommon, let's say, in astrophysics, but it's something, the use of LVF has a greater history in planetary science. And for example, there's this image of Pluto that you see here, where you see the methane features, was obtained through LVF, which was on board the New Horizons mission. And there was also one in ISOCAM. There's actually a small LVF also in Hubble Space Telescope, which was not much used. But anyway, it has a history in space already, but mostly in planetary science. Okay, so now how do we have this constraint that we want to really observe the focal plane across the sky, every part of the sky. And so how do we do that? So we design a survey that enables this, and the survey is really, there are a set of constraints. So this survey, you cannot point the telescope towards the sun, so it means you have to point away from half the sky, and you also want to point away from Earth. We are in low Earth orbit, we're in sun-synchronous low Earth orbit, so you want to point away from Earth, so which define, you have to look at the zenith roughly, and that's defined another cone of observation. And it's at the intersection of these two constraints led to, if you want, half a conical space where you can, which is really where you can point at any given time. And so we have to, and as we rotate over the sky, this allowed half conic structure will rotate, and so we have to repoint constantly repoint the system in this the telescope, sorry, to stay in this cone. And so this half cone is rotating all the time. And what we will do is that we do small steps as long as we're in these conic structures, and this conic structure is catching up. This constraint is coming with catching up with the pointing, and then we make what we call a large step to go ahead of this half conic structure, and then we do a collection of small steps, and then we repeat that. And so it's a very simple way of operating. We can really, we have designed it, simulated it extensively, and we can really pre-program it somehow. In practice, it will be, the commands will be sent a few days ahead, but it's really a simple way of operating, and we can really, and there is one way of operating. So we just operate this way. We operate this way for 2 years. And here you see if we do that as the Earth rotates around the sun, we will cover the whole sky, and that's how we can generate our whole sky survey. And so you see that this is after 1 year of observation. So we will have this is after 6 months of observation, sorry. So we'll have one full sky survey after 6 months, and then we'll have 2 more after 1 year, and we'll have 4 survey after 2 years. So does it make sense? Are there any questions? I will now switch to science. Are there any questions on this design choice?
So I have a question.
Yeah.
Why we are choosing this 96 bands, and how are these 96 bands are chosen?
Yeah. So yeah. So these bands are defined really to address. So we are in space. So if we wanted to do an optical survey, we don't need to go to space. So we really so we really want to be in an infrared. In infrared, it allows us to go deeper because of, as you know, the light is redshifted. So we can, by going to infrared, we can observe a more fainter, more distant object more easily. So that's really what set overall wavelengths. And after that, we select the wavelength so that we can have accurate redshift reconstruction. So we have a wide enough wavelength coverage to enable a full redshift reconstruction. And we also we have interesting feature in this band which are being redshifted throughout our band, which allow us to reconstruct redshift from this galaxy. In terms of the runization, the history, the origin of galaxies, we cover interesting feature related to the epoch of runization. In particular, we have the Lyman alpha emission, Lyman alpha cutoff, which will be clearly in our band, which is a very important feature. And also, we'll have the and for the ICs, within our band, we'll have the water ICs, the broadband feature absorption. I will describe that later, which are which are critical for our investigation. So it's a complex trade, but that's really the spirit. Does it make sense?
Yes. Yes.
Okay. So now I will detail a little more what we call the inflation investigation, which is really how we can probe the clustering of how we can learn about inflation by measuring the clustering of galaxies over the whole sky. Okay, so as you know, and you are all very familiar with this, of course, this is map.
Yeah, there are a couple of questions in the chat, I noticed. Vishrut, maybe you can just unmute. I hope you can speak, right? All this. So it says, what other advantages are there for the simple design? this was?
Well, yeah, advantages is that it's well, it's simpler to build to some extent, so more robust. So that's a kind of a robustness is a good thing, and it's a fast program. So yeah, as I said, the MIDEX mission are usually done on a fast schedule. So you have a limited amount for study, and you want something as simple and robust as possible. So that's really a key driver. We cannot afford, we don't have the time to do a technology development, so it has to be something simple and robust. I think that's really the key advantage.
Just a related question from me. I mean, so LVFs, is that a promising direction forward in terms of replacing spectroscopy with these kind of filters, or it is just that it works in this case and in these?
Yeah, so that's an interesting question. So I think there is more to do with them for sure. It cannot. I think it's so if you wanted to do typical high resolution, let's say a spectrograph like DAISY, well, a typical spectrograph have a spectral resolution about 1,000 or more, or 10,000, so much higher frequency resolution. So if we wanted to do LVF with that, in principle, there is a lot of freedom in designing the profile, the frequency, the wavelength dependent of your LVF. So you have a lot of freedom. You could potentially do it, but then it becomes more inefficient, because then you have to do a lot of small steps. You will have to map every single element. So then you will have 1,000 steps for to cover the full spectrum, and that becomes a step is it requires repointing, you need to slew the spacecraft, you need to stabilize it, so it becomes very inefficient. So I think you probably wouldn't make sense to go to very, very high angular resolution, but that's very high wavelength resolution. But I think you could easily increase by a factor of 10, and it would become still very competitive. And actually, there is a design that uses concept called what's called a CDIM, and you can look on the archives, our papers, where people, so I think Asanta Correa and Su-Ching Cheng were trying to develop something similar to do epoch of ionization, to really focus on the epoch of ionization, and but with a 10 times higher frequency resolution. But even with 10 times higher, you couldn't afford to do it. It was already difficult to do all sky surveys, so you had to do about 1,000 or 2,000 square degree only. So I think that's a trade-off. But on the other hand, it's really, again, the fact that it's a very simple to operate, fairly simple to build is a great advantage for space. So I think there is room for there was room for new ideas, and I know a lot of people have been thinking about it since. What can be done? And I think there is more to be done. Yeah,
so
it's not the answer to everything, but it's
definitely. I've heard this spectrometer on a chip being mentioned all.
I think it's I think that's
a
maybe,
completely separate concept, or
I think so. Yeah, I think so. Yeah, I think this is more. Yeah, this is more. I think spectrometer on a chip is like every pixel you have the full spectra, whereas for us, every pixel every pixel would see a single wavelength, and then you have to step throughout. Yeah. Does it make sense?
Yeah, thanks.
Okay. All right. So back to the CMB. Let me check the time. So I'm running. Okay. So Planck map of the sky, you see this beautiful map you see here, and as you know very well, the color fluctuations correspond to intensity fluctuation, which correspond roughly to density fluctuation at the time of recommendation. So when the CMB was emitted. So it's a beautiful map. Really, as you know, it's very amazing. And one of the by doing a characteristic detailed statistical study of this map, we can really learn a lot about cosmology, and we did. But so one of the remarkable feature about this map is the fact that if you were to simply do its PDF, and that's not an actual measurement, that's a simplification. But if you were to put an histogram, if you want a number of pixel hours temperature, it is very well described by a Gaussian curve, and that's really there's something very fundamental about that. There is something very fundamental about that is the fact that the fluctuations temperature fluctuation are actually Gaussian distributed, and it has to do with inflation, which is a period of exponential expansion at the very early universe. In a very early universe, that really stretch out quantum fluctuation. And so the fact that that this map is Gaussian has some very profound implications. And so, but in fact, according to Earth, we don't expect from inflationary model, we don't expect this map to be exactly Gaussian. We don't expect this temperature distribution to be exactly Gaussian. We expect a small skewness. And this skewness which is like an excess on one side, if you want. And we expect this small skewness to be proportional to a parameter we call FNL. So we expect what we call a small non-Gaussian distribution, so which is called, and this non-Gaussian signature really originates from early process at the time of inflation, some small nonlinear evolution at the time of inflation, which will create this skewness. And by measuring this skewness, by measuring this FNL parameter, you can really learn something very unique about inflation. And that's really what we try to do. So Planck measures this number FNL by doing this kind of analysis that I described very, very well. On SPHEREx want to do that much better. So that's really what motivates our inflation investigation. And I will now tell you a little more about it. So we want to improve our constraint on FNL by an order of magnitude when compared to Planck. I'll skip that, you're all familiar with that. But the key difference, as I said before, is that we want to measure this FNL parameter using the distribution of galaxies instead of measuring the CMB. And so, and why it is interesting is the fact that the CMB is a 2D surface, so it's a 2D signal. So and it's actually a band-limited signal. There is not much information on a smaller scale. So you have a finite number of modes. And if you go to 3D and if you characterize large-scale structure, if you've got a spectroscopic survey, if you have access to the third dimension, you can actually many more modes, and you increase the number of modes, and so you increase the statistical information, which let you improve on this constraint on FNL. Okay, so FNL typically is defined as a expansion of the primordial potential. Here you see, you can think of it as a Newtonian potential, but at the time of inflation, and you model this potential by a Gaussian part and a non-quadratic term whose amplitude is proportional to FNL. And so really, it's really, the inflation is driven by multiple components, multiple field, multiple inflaton, and different model will have different prediction for FNL. The simplest model for inflation will predict FNL to be about 10 to minus 2, so which is non-measurable, but more complex model with multiple field will predict FNL to be order 1 or more. And so FNL of order 1 is considered to be an important theoretically motivated threshold, and so we are trying to reach this threshold with SPHEREx. And so, and if we measure FNL to be order 1, then we can rule out single field inflation. If we don't, then we'll constrain dramatically single field inflation. Current limit by Planck, as I said before, this has been measured by Planck already, and the current limit are 0 plus or minus 5 at 1 sigma. And because of this limitation number of modes, for FNL, we expect even future ideal CMB experiment it will be very hard to do FNL better than at 1 sigma. So there is a limit, and but so there is a remarkable effect in a clustering of galaxies. And what you see here this time is the 3D clustering of galaxies. So you see the 3D clustering of galaxy as a function of 3D wavelengths here, and for various FNL value. And what you see here is that if you have FNL is small, you follow this continuous curve here. But if FNL is different than small, and here you have a large value, positive or negative, you see that you depart from this behavior on large scales, and you have what we call a scale-dependent bias. It means the distribution of galaxies will exhibit a deviation from this simple linear relation to the matter power spectrum, and this dependence will go like 1 over k square or q square, where Q is a 3D wave number. So it's a 1 over k square dependent. It means you have the deviation increase as you go to larger scale. And so if you want to measure this deviation, you really want to measure the clustering of galaxies in this at a low k here. And so you really want to probe the larger scale, which means you want to measure the whole sky. And that's really why we are building a whole sky survey. And again, to summarize the kind of inflation we want to, the kind of constraint we expect, what you see here in this two-dimensional parameter space, you see on the x-axis, you see the problem Gaussianity, FNL. On the y-axis, you see another interesting inflation-related parameter, which is the running of the spectral index, alpha S. And here you see the constraint coming from Planck. This envelope here corresponds to the 68% constraint coming from Planck. And that we expect from SPHEREx. Is constraint, of course, located at an arbitrary location. We don't know the answer, but from using the path spectrum of galaxy, we expect this curve here. Using the bispectrum of galaxy, we expect this orange contour here, and the combination will lead to this red contours here. And so that's really, you see the dramatic improvement of expected over Planck. And in the background, you see multiple colors. And the simplest model of inflation, slow roll inflation, for example, single field slow roll inflation are located here on these regions. Slow roll of inflation with multiple field would be located here. And a lot more more diverse model of inflation could be anywhere, let's say, within the Planck limit. So really, according to where this contours, this spherical constraints end up, we can really constrain dramatically inflation and potentially really rule out a single field slow roll inflation. So that's really the key motivation for our investigation. Okay, I'll just to say no, because I know you just really care about that. I think that we have a strong CMB heritage in SPHEREx, and I think the experiments was designed really like a CMB experiments. Like there is this philosophy which is really diffused throughout the project, and so it means we are very worried about systematics. We're thinking very hard about systematics, and we try to control them as much as possible in hardware design, and then to monitor them and mitigate as much as possible in hardware. And then, so what we cannot constrain by design, we will monitor somehow, and then we'll mitigate in the analysis. But there is really this obsession about systematic effects, which is, I think, very specific to SPHEREx. And it's something which is relevant for many, many aspects of the mission: the optics, the detectors, the readout, the survey design, the thermal system, etc. And so the survey is designed, the way we construct the measurement is designed so that we can do multiple consistency tests. We have multiple surveys. We will observe the fields on every part of the sky multiple times so that we can compare the measurement and test for systematics. And we will, of course, this way we'll be able to apply corrections to the data if possible. And there's, I think, something with, as an example, and I don't have time to elaborate, although I wish I could, is really about the way we will calibrate the system. We really design instruments so that it's very stable, and that's working out exactly, detailing the scale that the stability, the kind of stability we need for the instrument. It's something we can relate directly to the signal we want to measure, and directly related to the large scale signal coming from FNL. And so we really went from the sensitivity we want on FNN to the calibration stability, which goes directly to the temperature stability of the focal plane. And that's something we thought about very hard and implemented in design. So that's an example, and there are many others. But I just mentioned this slide because I know that's something you all as a group, you are all thinking very hard about also. I think interestingly, so I won't have time to detail too much, but I think it's interesting as the fact that we want to measure the large scales is actually interesting because it's something which is there are unique and novel challenges to tackle if we look at the large scales. And something which are, because we measure scales which are larger than existing spectroscopic survey or galactic survey, we really have to develop novel methods. Some have to do with the fact that we look at all skies, so we really cannot ignore sky curvature, as is usually typical do in existing galaxy clustering surveys. And we also, because we look at the larger scale, we actually measure uniquely what we call GR term, GR correction even a clustering of galaxies. And we have to, for example, there would be some kind of there are potential terms analogous to the Saxford terms that will appear. There are lensing becomes an effect on larger scales, and magnification in particular. So we have to model that accurately, and we have to validate that, because not only we will measure this thing, but if we don't model them accurately, we'll really have to, it will bias our FNL interpretation. So it's something which is, I didn't fully appreciate, but it's something we are really kind of feel like we have to solve all this problem from ourselves. I have a series, I'm very excited by that, but it's also very, honest, because these are new needs to some extent, we really have to do that ourselves. And validate that very carefully. We have to develop our modeling, which is exciting. Also, we are, in terms of redshift modeling, we are in some kind of intermediate regime between photometric redshift accuracy and spectroscopic redshift accuracy. For example, like a survey, like a DESI has very high redshift accuracy. So redshift errors are not really an issue for us. They are becoming more of an issue. So we need to find a way to model these errors and to understand that, which is in a novel way, in a new way. So that's something which is also interesting. So as a remark, we have a lot of new problems to solve, which is very fun and sometimes challenging, but it's an interesting also data analysis or modeling problem we have to solve. That's come with this new measurement we'll do. Some paper I will highlight, I don't have the time to, so we developed a new model for new, this is work led by Richard Feder, a student who just graduated at Caltech. We developed novel ways to measure or simulate redshift distribution of our galaxies. We also have been thinking very hard about spherical Fourier-Bessel bases, which is a way to do, which is a natural base to do a 3D decomposition on a sphere, which is really extending what is done for the CMB, but doing a 3D, and that's really in 3D. So this is a very natural basis where we can do a lot of nice things, and we can, it becomes a very analogous to a CMB experiment, but in 3D. And so, but then we have to work out redshift space distortion. We have to work the wide angle there in this space, wide angle effects, well, although they're naturally taken care, but we have to think about that carefully. And we also have to worry about GR effects. So all this is, we have a lot of papers on this, and you can look at them if you're interested in this. I think it's very interesting and something we have to develop ourselves, which is in particular, it was work led by Henry Gebhardt, you see here, Robin Wen, who is a graduate student at Caltech, and Chen Henrich, who is a staff scientist at Caltech. So a lot of interesting modeling and theoretical work going on also. And we even tried to look into the working in the bispectrum in a SFB basis, which turned out to be much more difficult, but nonetheless very interesting. Okay, so that's it for cosmology. Now, so let me give you a quick overview of our what we call the extragalactic background light investigation, which is really the part of our science investigation focused on trying to tease out signals from the EOR. So we're in a low Earth orbit. We will look at the north and south pole every 96 minutes. And so naturally we'll look at the sky in multiple ways, and we'll be able to do very high reliability maps. On the signal we are after is really can be understood the following way. So if you look at this map, which is an actual map coming from the Spitzer Space Telescope at 3.6 micron, a broadband map, 8.5 arc minute only, you see, of course, a lot of point sources, some stars, a lot of galaxies. And so one thing you can do, of course, is mask all the points you see, to mask all the points you see, and that's what you are left with. So if you mask all the point sources you see, you are left with this diffuse background, and you see there's this kind of correlated smooth background. And this correlated smooth background is actually all the unresolved light from very faint and distant galaxies. We call that extragalactic background light. Astronomers call that confusion noise. And people, for example, in a CMB world, call that infrared background, or cosmic infrared background, or CIB. Or since we are near infrared wavelengths, you could call that near infrared background. But so the key point here is that by doing a precise, detailed measurement of this background, and if by statistically character exam, you can learn a lot about the population of faint unresolved stars that create it, and this way you can really probe much fainter signals, very distant signals that you would if we were just looking at point sources. So that's what we're trying to do, and what SPHEREx will do in this regard is like this has been done. Again, I said it's kind of analysis technique has been done in Derby, in Planck, Acario, Herschel, and that has been done also in Spitzer. What SPHEREx will do in the near-infrared is extend very much Spitzer. So whereas Spitzer did this kind of analysis for 72 square arc minute on only 2 bands, SPHEREx will do that over 200 square degrees and 102 bands. So you have much more information, and we go to large scales. So the fact that we have a large area will allow us to go to large scale where we can model this signal with much higher accuracy because it's all linear. And so to give you an idea on the sensitivity we are after here, what you see on the y-axis is you can think of it as RMS in some angular scale. So it's really a variance in some angular scale defined by the multiple L between 500 and 2000 as a function of wavelengths. And you see the SPHEREx wavelengths between 0.75 micron and 5 micron, as I said before. And here we don't have the full 102 elements. We've been into 9 elements. On the purple curve corresponds to the best fit template given current data. And the current data are the following. You see the Cyber sending rocket experiment here in green, and you see the Akari node, which is Akari was a Japanese satellite. You see some measurements here in blue, and some Spitzer point I just referred to in orange. On the SPHEREx point here are the black points, but then of course what's unique about this point, the fact that whereas all the previous points here are all 1 sigma errors, the SPHEREx point are actually 100 sigma errors. So they are really statistical signal, the statistical information, the noise performances will be much better, and so we can learn much more about it. And in particular, we would like to separate all the low redshift signal to tease out the signal coming from the epoch of rendezvous, which we call EOR here, which is model predicts that it will be somewhere within this red envelope here. So this curve here corresponds to our expected noise performances. So you see that we are sensitive enough to be sensitive to the signal. But the question, of course, would be to separate all the other signals coming from lower redshift to tease out this EOR. So it's really in a CMB language, it's really, you can think of it as it's really a component separation problem. But we'll do that. So that's really, we are sensitive enough to see the EOR, but we need to be able to separate the low redshift signal. Okay, and so a lot of it can be done through through cross correlation with known galaxies, and I will skip that. I'll refer to this paper by Yunting Chang and Suqing Chang, detailing the ways you can use SPHEREx in cross correlation with other surveys like SPHEREx, DAISY, and Rubin to probe, to reconstruct this signal. And finally, I will just flash 2 slides and I'll stop. I'm running a little late, sorry. Just about our third scientific investigation, which is really about what we call the ICE investigation. And so on the question we are trying to address here, really, what are the conditions for life outside the solar systems? On the condition here, the fact is that life as we know it on Earth is sourced by what we call biogenic molecules, so water, CO, CO2, or methane. But most of this molecule, if you want to looking for life, would mean looking for this molecule throughout the cosmos. But actually, most of the ices in ISM, in interstellar medium, is in form of ices. So 99% of interstellar water is locked in ice. So if we want really to follow the water, to look for water, we really have to follow the ice. And so, and the key scientific question that drives this field is really, when we think at Earth, is like, where does the water we have on Earth come from? Actually, that's not a fully answered question. So did it come from asteroids or comets? And if this happened, when did that happen? And or did this come from asteroids coming from the Oort cloud or a Kuiper belt or so on? And so that's really the question. We unanswered question yet. And so SPHEREx can address this question by really conducting a survey of water ices throughout the galaxy. And so we look for signature of this water ices in multiple systems, would be molecular clouds or disk, etc. So we'll have an extensive study, extensive census of water ices. And the way we'll conduct this is really by looking at absorption features, broad absorption features in stars. So we have you have background stars. We'll measure a spectra because we'll measure a spectra of every object in the sky. We'll measure a spectra, and sometimes on line of sight you'll have another system like a dense cloud or a young stellar envelope or photoplanetary disk or young solar system. This system, which is on line of sight, if it contains water ices or water CO, water CO2, it will lead to a broad absorption features, which looks something like that. So here you see you see the broad water absorption, the broad water absorption in CO, absorption in CO2. And so we expect to measure this kind of spectra in more than 9 million of objects, 9 million stars. And so this way, we'll conduct a very statistically unbiased census of water ices throughout the Milky Way. And that's really how we will be able to address this question in another way. So to summarize, I think SPHEREx will create the first all-sky and infrared spectroscopic survey. It will be a quickly released data set of lasting legacy, and we expect many discoveries to come from the community. I think that SPHEREx offers and really relies on a very simple and robust design and modus operandi. It enables a high control of systematics thanks to multiple built-in redundancy, just a CMB way, I should say. And SPHEREx will enable multiple and powerful studies from opportunity to learn about inflation, extract galactic background lights to probe the reionization era, and also water absorption in stellar spectra to really probe the conditions for life. And so SPHEREx being all sky survey, it will overlap with all future and past and future surveys. So there will be clearly a lot of synergies with the future missions. And so this is going to be a very exciting decade. And that's it. Thank you so much for your time.
Thanks a lot for such a nice overview of SPHEREx. I guess there are some questions in the chat. So Mohit, do you want to unmute yourself and ask the question?
Hello. Hello,
Yes,
Oliver.
Yeah.
Am I audible to you?
Yeah, I can hear you well.
So I have actually very basic question. So the satellite will scan the sky one time or just 2 times or 3 times in the same way just WISE satellite does?
So it will observe we'll do a full sky survey. So we'll do a map of the whole sky 4 times in 2 years.
In 2 years, oh, okay, I got it. In 2 years, you will scan the full sky only one time.
No, we'll scan a full sky every 6 months.
Oh,
And then for 2 years, every 6 months we have a whole sky. And so every after 2 years we'll have 4 full sky survey. And it really come from, if you want to think of it as you think of the Earth, the orbit is such that we are on what we call the shadow line between it's called the terminator line between the shadow on the sun, the part of the Earth which is illuminated by the sun, on the part which is in the shadow. We are just at the boundary, which is called terminator line. And so you can think of it first order, we are just looking up, scanning like that. And as Earth rotates around the sun, this circle will end up covering the whole sky. And so that's why after 6 months, you have the full sky.
Okay, I have one more question. So the
Yeah.
parameter, known Gaussian parameter you have had, but the single field model assume that the fluctuation will be Gaussian like. So what are the basic motivation behind adding this known Gaussian parameter?
Yeah, so that's right. So we expect but basic motivation is that the fact that there will be either there is nonlinear behavior in a field, which lead to quadratic term if you want to, or nonlinear term in the potential, or you could, if you have multiple field, you could have also interaction across this field that will also lead to to this FNL parameter being a non-small. So it's really about probing physics of inflation, probing interaction across the multiple inflation fields, or it's about probing, if you want, the nonlinear evolution of the inflation at the time of inflation.
Okay, this is basically come from the fact that there are the multiple fields that can couple over, and the
That's right. They can interact in non-trivial ways, which leads to a non-zero FNL. That's right. Yeah.
Okay. Thank you very much.
Of course.
Vishrut, you want to go ahead, maybe? Vishrut?
No. So we went with this question earlier, right? So
Okay. There was some disturbance, so I'm not. Okay. Yeah, I think we went through this, why we have this broad absorption spectra, but
yeah.
Okay. Okay, so Raghav, do you want to unmute yourself and ask your question?
Hello, sir.
Hello.
Sir, I want to ask a question. Sir, what is photon shields?
Yeah. So what are photon shields? I guess I can show you a picture of them. Photon shields are these structures here that you see here. This photon shields here, and they have two goals. The first one is to protect the spacecraft, the telescope. As I said, it has to remain very cool because we observe it in the infrared. So we want it for it to be cool. It has to be protected from Earth shine, which is a light, coming from reflected from the light reflection coming from the sun on Earth. So we have to protect from that. That's this photon shield does that, but it also serves to cool the system by allowing radiation to very effectively escape in space. So it's part of the radiation system. Just allows it for the spacecraft to cool very efficiently. So it's part of the passive cooling design that allows the spacecraft to remain very cool. So they have this double, they have these two functions, and so it's really we have three conic photon shield, like 1, 2, 3 here, and here is just a cutaway, but it covers the full spacecraft. Does it make sense? Is it clear?
Yes, sir.
Great.
Majulu, please go ahead.
Hey, am I audible?
Hey.
Hello, am I audible?
yes,
Yeah.
I can hear you. Yes,
Okay.
we can hear you. Yeah.
Okay.
Sorry.
Okay. Thanks for a nice talk. So I have a question. So recently after the first year DESI results, we have growing interest in dark energy and varying equation of state. So I'm just curious, what will be the predictions or maybe the constraints that we can get from SPHEREx?
That's a very good question. I don't have a clear answer because we thought about it, but we didn't run forecast on that yet. So it's a very good question. So I think I'm hoping that with SPHEREx we can do we can have a very good probe of dark energy using BAO signal at low redshift, at redshift lower than 1. And I think the DESI results suggest that it's a very interesting region regarding the evolution of dark energy. So I'm hoping SPHEREx will be able to say something about that, but we cannot give you a quantitative answer yet because we have not run the full forecast for that. But if we should be able to do a very good BAO measurement of the whole sky, and that should really directly illuminate this question in a different way. So that's hopefully SPHEREx will be able to say something.
Okay, thank you.
Will the sensitivity will be comparable with the DESI forecast?
I don't have a quantitative answer to this yet.
Okay.
But it will be anyway. It should be an interesting measurement.
Yeah, Tarun, please go ahead.
Hi, Olivier. I just had a question about your the kind of limits that you would put on the extra background light, right? And its implication on UR. Just if you go back to slide, I mean, I'm I mean, are these on the same wavelengths at where UR is being probed, or I mean, am I missing something there? Or? You had this curve with this extraordinarily 100 times smaller thing.
Yeah. Sorry, I cannot go. This animation has to play. I cannot go. Sorry.
That's okay.
All right, I'm coming. I'm getting there. Here is this curve. Yes.
Yeah, this plot. So,
so SPHEREx wavelength coverage is between here, 0.75 micron, which is here, and here. But the OR signal is really coming from, models about what the emission coming from galaxies during the period of ionization. And here you see the Raman alpha emission, and here you see the Raman alpha cutoff coming from at high redshift between around 6. Yeah. But the differences, these are current measurements, right? And so you see there is a 2 orders of magnitude difference, and really the difference here really comes from all the galaxies, all the light emitted by galaxies at redshift between the redshift of EOR and us on 0. And so we have to remove all this signal to be able to tease this one out. And we can do that by because we have measuring we have this 102 maps, and we'll measure the autospectra on the cross spectra of all these maps. And so we will model the low redshift part to tease out the high redshift part if you want. And the fact that we have this full, it's the fact that we have this full correlation structure on a cross correlation structure let us reconstruct the redshift evolution if you want. That's a spirit, yeah. It's a kind of it's very analogous to the CIB analysis for Planck, where you measure the CIB at multiple wavelengths and you measure the cross correlation between the CIB, let's say between 270 gigahertz on 847, and you measure the auto, you measure the cross, and then you can constrain your CIB model, and that will do exactly the same thing, but with many more frequencies. So hopefully the model will let us get this at this EOR signal.
Thank you.
On a good paper, if you want, it would be the I didn't reference it here. Okay, this animation again. Sorry, there's a Fang paper that is one approach to do that, which I can send you a reference if you want.
Okay, sure. Thanks.
Mohit, please go ahead.
Yeah.
Sir, will we get the infrared background fluctuation map like CMB map from this as a data product from this mission?
So we will do in an infrared. We'll do diffuse map like the CMB maps, but in an infrared. So it's going to be light, mostly light coming from galaxies. But yes, it will be similar type of this kind of diffuse map. You see here the reddish colors. It will be you could think of it as a diffuse light map. The CMB is a diffuse light map, but here is just, of course, a totally different wavelength. So it's different processes. But yes, you can. It's really you can analyze this map like you analyze like a CMB map in terms of statistical tools. Yeah.
Oh, okay. Thank you.
I have maybe a nice question. So you were showing this scan strategy, right? Where it was taking like a big step, then like small step, then big step. And then it was like doing like full sky survey like that. Now, due to that, there will be this discrete set of sensitivity, right? The sensitivity will be smaller in the larger steps and things like that. And will that anyway affect any systematics or anything because of that sensitivity difference?
So it doesn't. So like it's a collection of exposure. If you want, you can. So if you look at this image here, we are taking exposure, multiple exposure within this half cone, but then the exposure duration, the sensitivity is always the same. So at the end of the day, the duration of each exposure is exactly the same.
I see.
The sensitivity is end up being pretty uniform throughout the sky. The details to first order is uniform, and then there are small variation, but it's actually very uniform. But if we, nonetheless, there are non-uniformity because we cannot observe. Sometimes there are other constraints that lead us to observe more or less certain areas. And if we don't account for that, this kind of variation in sensitivity, that could be an important systematics. That's correct. But then in principle, we know after the fact, we know exactly how long we observe in each part of the sky. So we'll have a very good sense of our sensitivity in every part of the sky. So we can correct for that. If we were not correcting for it, then it would be an issue. You're right. Yeah.
Okay. That's great. Okay.
Does it make sense?
any
Yeah.
other-
Okay.
Yeah, it makes sense. I didn't understand.
Great.
So this cone is actually moving, and that's why it has like same sensitivity. Okay. Yeah.
That's right. Yeah. That's right. Yeah.
Yeah. Tarun, please go ahead.
Yeah, just again, just prompted by this. So if you have these filters which are linear, aligned, you would visit the same part of the sky possibly in a different orientation, right? Or
That's
is
correct.
it,
Yeah. Slightly different.
and
That's right. Yeah.
does that give you any, I mean,
So
the relevant information, like if you see systematic differences, or would it be something you look for, or you just integrate them together?
right. That's I guess it doesn't matter too much because when you do for the whole sky, so we'll have a little bit of yeah. So let's say you would be a different part of the sky, different part of the focal plane, on potentially a slightly different orientation. But it's okay because you're looking at the way it works. You look at the flux in individual sources, so you do a local measurement of the flux in this source in this part of your focal plane. So so what you do is that you, for every wavelength, after the fact, you will look at these sources and you say, okay, I observe it here, at this time here, and then at this time here, at this time, and then you just measure locally if you want the flux. So it doesn't really, it's not necessarily the properties of the detectors, detail of the property of the detectors will vary across the focal plane, but then we will monitor that very well through different ways. So we know the variation of of the calibration or dark currents, kind of things throughout the focal plane, so we can correct for that in principle. In a deep field, when we do diffuse light, actually, as you know, just like for CMB, you actually want it's a good thing to have multiple orientations and multiple to control systematic effects or beam effects on far side lobes, all these things. So it's actually a good thing to have multiple orientation, and we look at the same field, and as we rotate, we'll just by construction we'll have multiple observation, and then it's really adds a lot of robustness to your reconstruction. Yeah.
Thanks.
Is there any other question from the audience? If not, let's thank Professor Olivier Doré again for such an wonderful talk and also answering our questions. We will end the meeting here. Thanks a lot, Olivier.